Hello there, welcome to a follow-up presentation on numerical solutions to ODEs. In this case, we are going to show a worked example using Eulers method. Before we do that, let's just recap what we saw in the previous presentation. Recall that we said if we've got a differential equation, dy dx equals to a function of x, y, as a function of two variables, which you cannot solve using analytic methods. The first thing we noted was that this equation leads us to saying dy is equals to f at x comma y multiplied by dx. You note here that if we've got a graph, let's say suppose with a graph of the solution of this function given this way, and then if we value here, let's say x0, and then we've got a y value there, which is y0. So if we add let's say a change in x, which is in this case this kind of stretch to this x, we get another point here which you can call y1. And if we draw a vertical line across x1 here, we'll get this point here giving us the level y1, which is the corresponding value of the function as x1. But that value y1, you must notice that it is actually y0 plus this change in y, which in this expression is given by dy. So in other words, if we wanted y1, we would then say y1 is equals to y0, this value at this level, plus this change in y. At the end of good day, if you look at this, what we've got here is that change in y is actually, the change in y itself is actually change in x multiplied by the value of the function. In this case, it will be x0 comma y0. And we recall that also we said we're going to denote change in x as h, which we call our step. In other words, if we want successive values of x is here, we simply need to add change in x, which is equals to h. So to get x2 here, we would add another stretch of change in x, well, then we get x2. But now what we've got here, we see that to get y1, we need y0 and x0. And in this case, the formula will look like y0 plus h multiplied by f at x0 comma y0. To get y2, we would need y1 following the same pattern here, y1 plus h multiplied by f at x1 comma y1. So carrying on this process, we can go up to saying get xn plus 1. If you need the next value y2, we need the previous value y1. So when we need yn plus 1, we would need yn, which will then yn would be yn plus h f at xn comma yn, which now we said this would be our general formula, which we call Eulers method. So this is what we saw then, which means to get the approximate values of this function, of the solution to this differential equation, we'll basically use this value and get table of values which you can plot to get an approximate graph of the solution to the differential equation. So here is the summary of the formula, or the Euler's formula, which simply tells that once we've got yn, we can get the next value by just doing the following calculation using the previous values. So now, here's an example which says solve the first order differential equation dy dx equals to y squared minus x squared, given that y0 is equal to 1 when x0 is equal to 1. This actually means that if we've got a graph, let's suppose the graph of the solution to this graph, this graph would pass through the point 0 for x and 1 for y. So which means this point is actually on the graph of the solution. So now proceeding to solve this, we simply need the formula, which is given this way. Now there are the values x0 and y0. So now we follow this formula, or this expression of f of xy, then we calculate the value for y1. So at this point, let's invoke our calculator. There is our calculator. So what we have here, we're going to simply say 1, which is y1, plus h in this case, the step, which is 0, 1. Actually, the problem doesn't state here the step, but in this case, I decided to choose to use h equals to 0, 1. You can use h of your own choice, even smaller than 0, 1. Let's say h equals to 0.01. In this case, you will basically be using a finer scale on your x-axis. So as you can see here, once you choose that h is equal to 0.1, from 0 you can add h, you get 0.1. There you add h again, you get 0.2, 0.3, 0.4 up to 0.5. Like you can see, this problem is supposed to be solved between 0 to 0.5. So now we need y1 at this point. Then we've got the 1 plus h times, we'll use brackets there. y1 is 1, you get 1 squared minus 0 squared. Close your brackets, equal. We get that, which means that the y1 here is 1.1. Now that we've got y1, we can proceed to get y2. And then let's set this y0.1 as our answer, which is y1 plus 0.1 multiplied by, in this case now y1, y is 1.1, so it's 1.1 squared minus x1, which is 0.1 squared. Then we get the answer to be 1.22. The next thing is to calculate y3. Then we get our answer, which is y2 plus 0.1 multiplied by f, which is this case y1 is 1.22 squared minus 0.2 squared, which gives us 1.36484. Then now we calculate y4. We simply repeat this calculation with this formula, using this formula. Then we take our answer as our y3, then plus h, which is 0.1 multiplied by, in this case our y3 is 1.36484 squared minus 0.3 squared, which gives us 1.5421188. Now, when you get to this point where you get a lot of the decimal numbers, you must try to get your values in as many decimal places as possible, so that to avoid rounding off too early, and that will introduce an error into your final answer. So if you, for example, I recommend that if I ask for the answer to 2 decimal places, simply work to at least 5, 6 decimal places. Then you round off at the end when you give your final answer. So in this case, you have given 1, 2, 3, 4, 5, 6, 7 decimal places. Now calculating our last value, that will be y5. We've got our y being 1.5421188, which in this basically is our answer, plus 0.1 brackets answer squared minus 0.4 squared. Then finally we've got here 1.7639318. So in this case now, we've actually completed the table, which basically represent the values of the solution between 0 to 0.5. So what we can do now, we can take this table and simply plot the graph just to have a feel of how the graph of the solution would look like. But in this case, in our case, we can use this on MATLAB, enter this table as a matrix, and then plot x n comma y n. So we enter two matrices, one matrix being xn, another matrix yn. We just name them conveniently, then plot that, we'll get the graph of this. So as you can see, this method is a very simple method which relies on using the formula accurately, just capturing your data correctly, taking the right values at the right time, and computing a complete table. Then after that, you can, if you've got a graph paper, you can just graph that, or you can use MATLAB and plot the graph, and then you can interpret and see what exactly is happening with the function. So this is one example of this method using Eulers method. Then I would like you to try this same example using a different step h and do the same thing, plot the graph and compare your graphs. So the most important thing you must notice that h, once you are given the initial value of x, you just simply add h to the initial value to get x1. After x1, add h, you get x2 until you get to the end of the interval. Then later, what follows is simply using the formula to complete the values of y. Then at the end, you can plot the graph of your solution to the numerical solution to the differential equation given. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Waswanim Sipa.